Hello, this is Ms. DB, and today we are going to learn about complex numbers and roots from Chapter 5, Section 5. We're going to learn what imaginary and complex numbers are and use them, and then we will solve some quadratic equations that have complex roots. All right, so if we're going to graph f of x equals x squared plus 1, it's the parent function moved up 1 unit. So it has no real zeros, meaning it never will go through the x-axis. If we were to set this equal to 0 and try to solve for the roots, we'd have x squared plus 1 equals 0. So x squared is equal to -1. And then we would solve that by taking the square root of both sides. When you take the square root of a number, like if let's say it was 4, you actually get two answers. You would get 2 and you'd get -2. Just a reminder, because -2 squared is 4 and 2 squared. When we take the square root of a negative number, though, we've never learned how to do that before. So we would get x equals plus the square root of -1 and x equals negative the square root of -1. But what does that mean? So up to now we would have to say, well, there's no answer, it's not possible. But mathematicians said, well, that doesn't work. We can't just stop at that point and say it's impossible. So imaginary numbers were invented. Imaginary number is the initial I, and it is equal to the square root of -1. So now we have answers for the roots of this quadratic. It would be I and -I. The square root of -1 is I, and we have one of those, and then we have a -I. All right, so we are now able to deal with negative square roots, because -1, the square root of -1, we let be I, and then we can figure out more things from there. One of the things that we can figure out from there is fractals. This is an example of a fractal. And this is based on complex numbers. Complex numbers is when you put an imaginary number with a real number, something like this. If you put one complex number squared plus another complex number, and feed back into z over and over and over again, you get this Dehn-Brastad, which is really cool. So there are applications, many applications of imaginary and complex numbers. All right, let's add the complex numbers to our sets of numbers that you've already learned about. So natural numbers is when we start with 1 and 1, 2, 3, 4. The whole numbers are the natural numbers plus 0. So there's only one more number. The integers include the natural numbers, include the whole numbers, plus the opposites of the natural numbers. So -3, -8, -4, and so on. All of those are the integers, so these plus these. Rational numbers is a number that can be written like a fraction, like 7/5 or 8/1, which is also an integer, but that can be written as a fraction. It includes decimals, it includes negatives, it includes decimals that repeat, like 1.244, but it doesn't include decimals that never repeat. The irrational numbers, see this line separating them. There's no subsets of the irrational numbers, but it's pi and -5 and so on. All of these types of numbers, the irrational plus the rational, and all the subsets in the rational, make up the real numbers. So far, up to now in your math classes, you've just dealt with real numbers. Now we're adding to this. So I'm putting another bigger box around here. And these are the complex numbers. So the complex numbers do include the real numbers, but also the imaginary numbers, which is I, and things like 3i and -I, and so on. And the complex numbers, which is an imaginary plus a real. So like 5 plus 2i, -7/2 minus I. All of those are complex numbers. So I guess imaginary numbers would be a little subset in there. And now you've got pretty much every number you could think about is part of the complex numbers. So we just broaden what you know about numbers. An imaginary number is the square root of a negative number, remember this, memorize this, that I is equal to the square root of -1. They can be written as bi, where b is a real number, so you can have an imaginary number like 3i. The square of an imaginary number is the original negative number. So if you have I times I, what do you think that equals? It equals -1. Here's why. If you take the square root of -1 and square it, squaring a square root undoes it, and you end up with -1. So I squared is equal to -1. That's also very handy to remember. All right, so what we're going to do is we're going to simplify roots. Now you practice simplifying roots in quarter 1. You should have, in chapter 1, you should have learned how to do this in Algebra 1 anyway. So if we were going to simplify the square root of 121, you would say, well, let's see, what times what equals 121? Oh, that's a perfect square. The square root of 121 is 11. We have the square root of -121, and then it's 5 times that. So what we're going to do is rewrite this as 121 times -1. It's still the square root. Then we can write that as the square root of 121 times the square root of -1. That's helpful because we know the square root of -1 is equal to I, the imaginary number I. We know the square root of 121 is 11. 5 times 11 is 55, and the square root of -1, finally they put it as I. So the answer to this would be 55i. Let's do another one. Square root of -96. Now that's not a perfect square, because I know that like 9 times 9 is 81, 10 times 10 is 100. So it's somewhere between 9 and 10. We do not use our calculator and get a decimal version of this. Do not do that. But I was just checking to see if it was a perfect square. So instead you might think about, well, what perfect squares might I be able to divide into this? Let's try 4. Let's see if 4 will evenly go into 96. That'd be 8, 16. Yeah, 4 times 24. Well, that's helpful. I think 16 would have gone into that. So you look for, yeah, because this would be 4 times 4 times 6. So you look for when you can find a perfect square. So 96 could be rewritten as the square root of 16 times 6. And then we'd have the square root of -1 here. I do this because I know what the square root of 16 is. The square root of 16 is just 4. So now I can simplify this, and I would get negative because of this negative, 4 because of the square root of 16. I still have the square root of 6. I know what the square root of -1 is here. I'm going to replace that with I. Now, you might start by writing it like this, -4 square root of 6i. This I looks like maybe it's underneath the square root. We always take the I and move it in front of the root, and then it would be right after the -4. So here's a better way to leave your answer. -4i times the square root of 6. All right, how about the square root of -12? This is one from your worksheet. So we can start by rewriting this as the square root of 12 times -1. And that is equal to the square root of 12 times the square root of -1. And now you have to simplify the square root of 12. So you might think, well, 12 is 6 times 2, but that doesn't help me. I need to rewrite 12 as the product of two numbers where at least one of them is a perfect square, and that would be 4. So it's going to help me because now I can say, well, I know what the square root of 4 is. The square root of 4 is 2, and I can't simplify the square root of 3, but I am going to be able to simplify the square root of -1, because I know that's I. And again, put the I not here, but right after the 2. So you'd have 2i times the square root of 3. All right, how about 2 times the square root of -36? This one's fun because we know the square root of 36 is just 6. So this one's going to simplify quickly. 2 times 6, and then you'll have the I after that. So 2 times 6 is 12, so 12i, this simplifies too. All right, here's some examples from your worksheet. You can see that number 1 and 2 have been started, just like we just did. Let's do number 4. Okay, so 5 times the square root. I'm going to put the negative 1 at the back, just like they did. And now I have 54. What times what equals 54? So 6 times 9 equals 54. Is that the best thing that I could use? I think so. So I'm going to write this as 9 times 6 times negative 1. Now simplify this by rewriting each of these with their own square roots. And then 5 is just 5. The square root of 9 is 3. We cannot simplify the square root of 6. We can simplify the square root of negative 1 as I. Put these two parts together. Put the I over here right after it. And there you go. Here is that problem simplified in terms of I. Okay, so next thing that we're going to do is, now that you know how to simplify roots that have a negative in them, we are going to solve quadratic equations that might have an imaginary solution. So here we have x squared is equal to negative 144. It already has the x squared on one side and the constant on the other. So this one is ready to go. We're going to take the square root of both sides. Remember that when you take the square root of both sides, you need to take plus or minus in front of that. There's really two solutions when you take the square root of a number. And the square root of 144 is 12, so we would end up with, I'm going to write that a little bit farther out than they did, like this, and then this would be 12, and this would be I. And it would be plus or minus because we're solving for x here. In these problems back here, we only did the positive because we were looking for the main answer. So then we just deal with the positives. But when we're looking for the solution to an equation, we have to consider both of them, because if we plug this back in, both of these work, and we would get negative 144 for both sides. Okay, now in this problem, it's not yet ready to go. So what we have to do is first subtract 90 from both sides, or add negative 90. Now we can divide both sides by 5, and we get x squared is equal to negative 18. Now to undo a square, we take the square root. Now we have a similar problem to what we worked with before. The square root of negative 18, we could write that as the square root of 18 times negative 1. 18 is equal to 9 times 2. So I can take the square root of 9 times the square root of 2 times the square root of negative 1. So you'll see that this will simplify to 3i times the square root of 2, because there's the 3, square root of 9 is 3, this is the I, and then the square root of 2 can't be simplified. Don't forget that it's plus or minus. There's going to be two solutions to these problems, the positive and the negative of each. All right, so in this problem, we have to take the square root of both sides, so we'd have plus or minus the square root of negative 36. That's the same as 36, square root of 36 times the square root of negative 1. Square root of 36 is 6, square root of negative 1 is I. That's it. So this is an easy one. All you have to do is take plus or minus 6i for your solutions. All right, here we go. We did a problem similar to this already. X squared plus 12 equals 0. So our first step would be to subtract 12 from both sides. And we'd have x squared equals negative 12. Then you take the square roots of both sides, and then we simplify that. So this would be, equal sign, plus or minus 12 times negative 1, which is the same as, we did 12 before, remember? We wrote that as the square root of 4 times the square root of 3, and there's the square root of negative 1. So this would be equal to x equals plus or minus 2 times square root of 3i. So x equals plus or minus 2i square root of 3. Putting the I right after the number. All right, so to check your work, you would put the answers back into the expression. 2i square root of 3, square it, add 12, and see if we get 0. So let's see, if we're going to square 2i times the square root of 3, I have to square each part. So 2 squared is 4. I squared, that's negative 1. Square root of 3 squared is just 3. So this would be 4 times negative 1 times 3. So 4 times negative 1 times 3 is 12. And oh no, it's negative 12. Negative 12 plus 12 is indeed 0. So it works if it is a positive. Let's check the negative. That would mean that would be a negative there, but negative 2 squared is still 4. So everything else would be the same after that. So it works. Checks. Both answers work. In this example, we would start by subtracting 25 from both sides. Divide by 9. Yes, it's a fraction. That's okay. Now we're going to take the square root of both sides. Yes, the square root of both sides. And when you take the square root of a fraction, that's the same as taking the square root of the top number over the square root of the bottom number. The square root of the numerator over the square root of the denominator. We can simplify the square root of 25 as 5. We can simplify square root of negative 1 is I. And we can simplify the square root of 9 is 3. So we end up with x equals plus or minus 5/3 times I. Or you could write 5i over 3. That would be the same. All right, here's another a little bit simplified picture of how the complex numbers fit into, or how the real numbers fit into the complex numbers. But we already talked about that. Every complex number has a real part and an imaginary part. Sometimes the real part might be 0. Sometimes the imaginary part might be 0. That's how we're able to write pretty much all numbers as a complex number. Real numbers are complex numbers when b equals 0. Imaginary numbers are complex numbers where a is 0 and b is not. Two complex numbers are equal if and only if their real parts are equal and their imaginary parts are equal. That makes sense. All right, now we're going to move on and we're going to do a little bit more complex work. This is going to include completing the square, which we learned about in the last lesson. So let's say that we have the quadratic x squared plus 10x plus 26, and we want to find the zeros of this. So the zeros, for these examples in this lesson, we might get complex numbers for the zeros. So the first thing to do is set it equal to 0. Sometimes that part will already be done. Now, this one is not factorable. So we would check to see if we could factor it, and I've already checked, and you can't factor this one. Therefore, we're going to try to complete the square. So, in the last lesson, you learned how to complete the square. We start by subtracting 26 from both sides. And now we're going to add something to both sides in order to make this be a square. So we want to complete the square. We want to make this something squared times something squared equals whatever we get on the other side. So to complete the square, we take, this is our b, we take half of that, and then we square that. So b is 10. 10 divided by 2 is 5, and 5 squared is 25. So we added 25 to both sides. So we take the middle term, take half of it, and then square it. Now this is something that is a perfect square. We could try, now we can factor this. This is 5, this is 5. So we can write this as x plus 5 squared. And on the right side, we simplify and we get negative 1. So then our next step is to take the square root of both sides in order to solve for x. And we're trying to find x. So I'm going to take the square root of both sides, but you can see that we're going to have the square root of negative 1, which is the imaginary number I. So we take the square root of both sides and we get x plus 5 is equal to plus or minus the square root of negative 1, which is I. So I'm going to rewrite this as I. So then I would have x plus 5 is equal to plus or minus I. And then the last step is just to subtract 5. Now, you could write plus or minus I minus 5 as your answer. But the way the complex numbers work is they always put the real number part first and then the imaginary number. So this is the preferred way to write a complex number. Real number and then the imaginary part. So you'll get a good review here of completing the square as well as using complex roots. Here is another example, x squared plus 4x plus 12. So the first step again is to set it equal to 0. Second step is to check if you can factor it. And in this one again we cannot. So then we subtract 12. So now we are ready to make this be a square by completing the square. We want to make the left side be a perfect square. So to make the left side be a perfect square, we take half of the middle term and square it. So half of 4 is 2. 2 squared is 4. So I'm going to add 4 to both sides. Then I simplify. On the left side, now I can factor this. This would be x plus 2 times x plus 2, which we can write as a square, is x plus 2 squared. On the right side, we have negative 12 plus 4 is negative 8. Now we're ready to take the square root of both sides. So we would take the square root, and we would get x plus 2 is equal to plus or minus the square root of negative 8. But the square root of negative 8 could be written as the square root of 8 times the square root of negative 1. That's I. This we could rewrite as the square root of 4 times the square root of 2. So we would have 2 times the square root of 2i, and then we'd put the I right there. So we're going to get, I wonder if they just write the whole thing. They do. So we would have x plus 2 is equal to plus or minus 2i times the square root of 2. And then we would have to subtract 2 from both sides to get this. And the negative 2 would go in the front, plus or minus 2i times the square root of 2. Okay, here's an example that's from your worksheet. First of all, again, set it equal to 0. Second step, subtract 13 from both sides. This is not going to factor again. Now we need to complete the square on the left side. So we take half of 4 and square it. That's 4 again. So we add 4 to both sides. That means that the left side is now factorable. It'll be a perfect square. So we'll write that as x plus 2 squared. And then negative 13 plus 4 is negative 9. Next step is to take the square root of both sides. So now we would have x plus 2 is equal to plus or minus the square root of negative 9. But the square root of negative 9 we could write as the square root of 9 times the square root of negative 1. Square root of 9 is 3. Square root of negative 1 is I. So this is going to be x plus 2 is equal to plus or minus 3i. And then to finish it, you would subtract 2 from both sides and put that in front, plus or minus 3i. All right, one more problem. We have g of x equals x squared minus 8x plus 18. So we're going to set that equal to 0. Subtract the 18 from both sides. Take half of the middle term of negative 8 and square it. Half of negative 8 is negative 4. And negative 4 squared is 16. So you would add 16 to both sides, which would mean that then on the left side you would be able to write that as a perfect square. So you can see then you take the square root of both sides, and I'm going to let you finish this one up on your own to find out what x will equal. All right, one last little tiny thing to talk about is that every complex number has a conjugate. What that means is all you have to do is take the opposite sign of the imaginary part. So the real number part stays exactly the same, but the imaginary part gets the opposite sign. That's it. That's all there is to conjugates. So for example, if you have that one of the roots is 8 plus 5i, the other root would be 8 minus 5i. That's it. If you have 6i as one of your complex or imaginary numbers, then the conjugate to that would be negative 6i. So it's the opposite sign of the imaginary part. That's all a complex conjugate is. So that part's really simple. You have a couple of those on the worksheet. So that is it for today. This is kind of fun stuff, and you will be using it for the rest of the year. So enjoy, and let me know if you have any questions, and thank you very much.